Hello students, today we're going to be talking about the image intensifier and what it does and the reason why it does what it does. So here's just a little something fun for you on fluoro. There's a lot of objectives that we're going to be covering over the next probably 2 weeks, and we'll be covering these in lab in addition, so it won't just be here in this lecture and all of these objectives. So here is your basic fluoro room. When we look at this layout, we see that we have a table. This is the under the table tube. You see your II up here. We have a floating tube up top, and we have the monitors. These are nice flat panel monitors. We're going to be talking about monitors in the weeks to come. So here's a picture from Bouchon. You probably recognize him here on the table. So here is your X-ray source within the table. We like this model because it has the metal that's part of the table that helps as shielding to protect you, the occupational worker, and the radiologist. So your patient lies here. Here's your image receptor. Here it's called the image intensifier, or your II. The older units had television cameras. There are some units still out there. It's some very old facilities. It's gone to digital imaging now, like our room that we have. So we will talk about the TV cameras, not in this lecture, but I believe next week. So you'll learn all about what happens after the II. So today we're just going to talk about the II. So the image intensifier, it's an electronic device that receives the image forming X-ray beam and converts it to visible light. So in conventional fluoro, without image intensification, there are two big, huge limitations. So one, it produces a statistically inferior image, and the light is too dim for our daylight vision. So historically, radiologists had to go in a dark room, wear special goggles to adapt to the low light of the image intensifiers. So the whole reason that we have these image intensifiers is to make the image bright enough. So when we look at the image intensifier design, it is a evacuated glass tube or envelope. It provides structural support for the objects inside of it, which we'll be talking about, and the glass tube maintains the vacuum, and it's mounted inside of a metal housing or container to protect it from rough handling or breakage of the tube. So very important for you to remember these next four things. The vacuum tube contains four basic parts, and these are what we're going to be studying in this lecture. So number one is the input phosphor and the photocathode. They're two separate things, but they're stuck together, so they consider it just one item. Number two is the electrostatic focusing lenses. 3 is your accelerating anode, and 4 is your output phosphor. The first generation image intensifying tubes had silver activated zinc cadmium sulfide crystals in the input screen. They didn't amplify the light like our new generation, the second generation, and this is typical for what we're using today. Some of the flat panels are a little bit different in the DR, but we'll cover that later on. So typically most systems in the hospitals have the second generation intensifying screens that contain cesium iodide. So CSI input screens are usually used. Like we have that in our lab currently. So we're going to talk about the input phosphor. The input phosphor is the first thing that intercepts the X-ray photon in the remnant beam. So it transmits through the glass envelope and interacts with the input phosphor. The energy of the photon is converted to visible light. So this process is just like our intensifying screens, same idea. So how does it do this? The fluorescent material is deposited on a thin substrate on the glass envelope. It hits the X-rays hit it, and it gives off light. The purpose of converting incident photons into light is so that we can amplify the signal, so amplify the light, so it's easier for us to see. So cesium iodide crystals on the output phosphor are approximately 5 micrometers in diameter and are packed tightly together. As you can see here, you can see how tight these are. They result in a microlight pipes with little dispersion, so this design is ideal for improving spatial resolution. So the photocathode. So the distance between the input phosphor and the photocathode is minuscule. So there's just adhesive and the two are bound together. So the adhesive is transparent. It's important to know that. So the photocathode is made up of a combination of antimony and cesium compounds. So what it does is it receives the light from the input phosphor and it emits electrons out. So photoelectrons is another name that we may use. So it emits the electrons in proportion to the intensity of the light that it receives. This process is called photoemissions or photoelectric emissions. So here's an example of your intensifying tube with its components. As you can see here, the input phosphor is right, so that you can see here the photon comes up and in to the input phosphor. So we'll start off with this one here. So the input phosphor is the yellow, the orange is the photocathode. And then you can see the electrons. This would be electrons coming through to a focal point. These little lines here are electrostatic lenses. We're going to talk about those. We're going to talk about the focal point and the anode with the output phosphor. So here's just a picture from Bouchon and a picture from Carleton to give you kind of the idea. We'll talk about the amplification later. So here is your input phosphor with your photocathode. Here they have them in just reset a little bit, which is fine. Coming through, these are photoelectrons and they go to the focal point. And here's your anode, and we're going to talk about how it has a hole in the middle. That's so that the electrons can come through at the focal point. And here is your output phosphor. The idea is to take one one electron and amplify it so you get a lot of light coming out of the output phosphor. We do that by accelerating the electrons. So the photocathode is also the cathode of the image intensifier. So it's kept at ground potential. So electrons are sped up by accelerating anode, giving a very high potential difference. So they apply 25,000 volts, and that pulls the electrons at a very, very rapid rate. So the voltage or difference in the electrical potential between the cathode and the accelerating anode, the electrons transverse the tube towards the output screen at a high rate of speed than they would have when they entered. So these lenses, the lens's responsibility, it's located after the photocathode, and they're along the length of the image intensifier, which is 50 cm long. So as we increase the voltage, the lenses will direct the electrons to the focal point, which is a very fine beam. So it comes in nice and wide, and these electrostatic lenses push the electrons to a focal point. So they arrive at the output phosphor with the kinetic energy and contains the image of the input phosphor. Okay, so in a minified form. So what happens is the image that is on the output or on the input phosphor is accelerated and minified. So when it hits the output phosphor, it is a lot brighter. So the accelerating anode is located at the neck of the image intensifier. It's a circular plate with a hole in the middle so electrons can pass through to the output phosphor without interacting with it. It accelerates and draws electrons from the photocathode and accelerates them towards the output phosphor. So here it is again, the potential difference is 25,000 volts. Very important. And here's a diagram again in case you forgot. So we're going to come into the input phosphor. So it's going to take the photon, change it to a light photon. It's going to hit the photocathode and be converted to an electron. It's going to come out and be pulled by the anode at 25,000 volts. So it's going to pull the electrons across. These electrostatic lenses are going to focus it into a fine beam to the focal point. and then it's going to hit the output phosphor. So we're going to talk a little bit about magnification and how the focal point will change based on the charge of the lenses. That's in our next lecture. So this is your basic II there. The output phosphor. So when the electrons strike the output phosphor, the energy is converted back to light photons. So it goes X-ray to light photons to electrons, electrons back to light photons. So thousands of times brighter than the input phosphor due to its smaller size, that magnification that I talked about in the last slide, and the additional energy given to electrons as they're accelerated to the image intensifier. So that's that 25,000 volts. Usually made of cesium cadmium sulfide. Most modern intensifiers are constructed with a 1-inch output phosphor. So all the current output phosphors are 1 inch. So that is all I want to cover for the II in this lecture. Our next lecture, I'm going to go into the different flux gain and what happens when we start using magnification. So there'll be some math involved. So we're going to end here on the output phosphor. So the basics of the tube here. So we've got the X-ray photon coming in to the input phosphor. The input phosphor is going to convert the X-ray to light. It's going to hit the photocathode. The photocathode is going to take that light and convert it to electrons. The electrons are going to come out of the photocathode. They're going to be accelerated by the anode with 25,000 volts across the tube, which is 50 cm long. You have these electrostatic lenses which are applying a charge that's going to take this beam and make it narrow to come to a focal point. And it's going to, once it hits that focal point, it'll hit the output phosphor. And once it hits the output phosphor, they're going to be accelerated due to the anode and the 25,000 volts. It's going to hit the output phosphor at a smaller image, so the light is going to be brighter. The output phosphor is 1 inch in diameter, and it's going to take the electrons and convert it to light. Okay, so that's the basics of the input phosphor. I hope all of that helps and makes sense as we move forward.